Okay, welcome to this new unit of work called the antiderivative, and you will see it in lots of places because that's a brand new name for our course, most commonly known as integration. Okay, so let's have a look at what this question's asking us to do. It says, given the sketch of the derivative below, sketch the original function. Okay, our key verb for this is sketch. All right, so we're going to produce this graph, and what we're going to do for this is we're going to be doing the opposite to what we've been used to, where we've been given original functions and being sketching derivative. We're going to be going in the opposite direction. So the first couple of points to consider are these two values here, because in the derivative function, where it cuts the x-axis means that there were turning points in the original function at that point in time. So what this means is we may have a maximum over here or a minimum over here, and a maximum over here or a minimum over here when x is on that second value. What we're going to do is now have to figure out where each one of these things actually occurred. Okay, so nice clean slate here because we've got to think about a few things. In the original function, if it was increasing or going in a positive direction, then our derivative function would be sitting above the x-axis. So these points over here, from here on and from here on, that means the original function was moving in a positive direction at that time. So this means it's moving up in a positive direction until we reach this point here. That's going to be our turning point. And again, moving away up this way in a positive direction. Okay, so what this means is this is going to be a maximum turning point, and down here this will be a minimum turning point before we start moving in that positive direction. Okay, so nice curved line, turning away. Okay, so there is the original function when given the derivative. All right, sorry, it's a little bit messy at the top there, but it's painting a nice clear picture. But wait a minute, could this also not be the original function if we just move this maximum turning point a bit higher and this minimum a bit higher as well? Right, it's still the same function, just shifted up a little bit. And we're still using those ideas of when the derivative function is going above the x-axis, that original function was positive or increasing. The same could be said if we went below, turned around and came back up positive again. Okay, so when we are moving in this opposite direction, we have something that can change. We can still get that shape of our original function when given the derivative, but there's something else that's happening that we're just not sure of at the moment. So we really have an infinite number of solutions from this, given that you do follow those turning points and you have the graphs moving in the right direction. We just have this graph moving up or down the y-axis. Okay, since we've discussed the graphical nature of the antiderivative, we're now going to look a little bit more about how it works algebraically. So in each of these examples from your student workbook, you are asked to differentiate a function first, and then hence work back in the other direction to find the primitive function. Primitive meaning function before it. So in example 2, we've got to differentiate x squared. So just like before, normal differentiation, 2 comes out the front, drop 1 off the power. Now what we're asked to do is find the primitive function of 2x. So now hopefully what we can see is if we go back up the chain, if the derivative function is 2x, the function before it, the primitive, is x squared, because we just differentiated x squared to get 2x. Okay, in example number 3, we've got to differentiate x squared plus 5. Okay, so same as before, the x squared part becomes 2x. Now this is the important part. That 5, that constant by itself, gets absorbed in this process, doesn't it? We can't differentiate the 5, so it just gets absorbed and has disappeared. This means that the primitive function, the level before that first derivative, is y equals 2x, but in this case we were told, we know that it had a plus 5 attached onto the end. The differentiation of that hasn't told us about that plus 5. It was given to us in the question. Okay, and again the last one, differentiate x squared minus 3. So that's going to be 2x. And again, hence find the primitive function for 2x. So this means the level before it in the chain is going to be x squared. And we're told it's minus 3 in this case. Okay, in example 5 and 6, we're asked to find the primitives of functions. Okay, so our key verb for both these questions is find. And what we're being told to do is to find that primitive function of x, and in example 6, 2x. Okay, so what this word primitive means is we're going to move back. All right, so just as if we would talk about primitive people or things like that, we're talking about people that from our past haven't got as high a civilization as our current world that we live in. So to do this, there's another way we'll learn later on, but to do this for now, let's think about something we do know. The derivative of x squared. Now we know that is 2x. And we know the derivative of x squared on 2 is going to be x, right? Or really 2x on 2, which is x. Now we are asked for that. We're asked to find the primitive function of x. So that means the primitive function of x is going to be x squared on 2. Now here's the big part. Plus potentially something else. What we call that is a constant value. Okay, so in this case we weren't given the derivative. We're asked to find the primitive of a function. So we've got to add the constant onto the end. And that constant number could be positive or it could be negative. Okay, now again for example 6, this one's actually a bit easier because we know some things about 2x. We know that the first derivative of x squared is in fact 2x. So this means that the primitive of 2x is x squared plus a constant. All right, because we do not know if there was a number there with attached to x squared, because in that differentiation process, going from here, from the to find the first derivative of x squared, there could be a number on the back that has been absorbed by that process, and that's what this plus c is for. We must always include that from now on. Okay, example number 7. And common theme, it's a find question, the key verb being find. This time we're being asked to find the primitive function. So again, we're going to have to go back, all right, or work in that other direction with our calculus to which we're normally used to. If the first derivative equals 5x to the power of 4 minus 4x squared plus 3. Okay, so if we need to find the primitive function and we're given the derivative, that means the primitive function will be the original. So we're given f dash x, the primitive of that will be f of x. Okay, so now we're going to think about how we're going to be able to find that primitive function. And to do this, there's a little idea presented to you in your student workbooks that says when given the derivative of a function, x to the power of n, then the first or original value, you're going to add 1 to that power at the top, and then that new power you've created, you're going to put as a fraction underneath on the denominator. Quite simple when you do some practice. Okay, so let's do the first one nice and slowly together. derivative function is 5x to the power of 4. So to this, we leave the 5 there. We're going to add 1 to that power of 4, so it's going to become power of 5. And then we're going to divide by that new power we just made, which was a 5. The second part, we have minus 4x squared. So I'm going to write the minus 4x down. We're going to add 1 to the squared to the power of 2, which makes it power of 3, and then simply divide by that new power. And the last part, we've got a plus 3. So I'm going to write my plus 3 down. Now it's got nothing attached to it, so it becomes x to the power of 1. All right, so we can leave it as it is because 3 divided by 1 is just 3. But the thing that we now must not forget is there could be potentially something else in this original function that has disappeared at the top here, and that is another constant. So now just to tidy things up a bit, this 5 and 5 cancel out, so we're left with x to the power of 5 minus 4x to the power of 3 on 3, that doesn't do anything for us, plus 3x plus c. And we've found the original or primitive function. With example number 8, we're given the equation of the gradient of a curve, and then it says if the curve passes through that point 1, negative 3, find the equation of the curve. Okay, so our key verb again is find, and we're given the function of the derivative, and we're asked to find the equation of the curve. So we're going to be looking back at the original equation. So this one tells us we're going to have to use the antiderivative or integrate, however you want to say it, and move backwards again. Okay, so we've got the gradient of the function, and we're going to integrate, we're going to move back. All right, so to that, we're going to leave the 6x there. We're going to add 1 to the power and divide by that new power. The same with the 8x, we're going to add 1, and I've got an imaginary 1 there, so that becomes 2, and divide by that new power. Do not forget to add a potential constant on the end. Okay, so now that we've got this, let's just tidy it up a little bit. And there is the equation of the original curve. However, we've got that c there. Okay, so we're going to be able to unlock that value of that c because we're told that it's also going through that point 1, negative 3, where 1 is the x value and negative 3 being the y value. So let's go and substitute those values in to our equation of our new line here. Okay, so there we go. We've substituted the x and the y value into the appropriate spots. Now we can go and solve to find c. And there we have c being equal to negative 9. So all we do now is we make our final statement. Therefore, the equation is y equals 2x to the power of 3 plus 4x squared. And then this is where we put in our value for our c, which is minus 9. Okay, question 9. And there's a little bit to digest in the start of this one. So it says we've got the second derivative being 6x plus 2. And then this is a little bit of a tricky part. It says when the first derivative is substituted in for the value of 1, and for when the original function is substituted in for the value of 2, they both are equal to 0. All right, so it's two kind of statements written together as one. And then what the question is actually asking us to do, the key verb, is to go and find the value of when the original function is 3. Okay, so if you think about the chain of events here, we're going to be starting with this second derivative, and if we work backwards, it will give us our first derivative with a plus c on the end, and if we work backwards from there, it'll give us our original function. Okay, so essentially we've got two chains of integration that will be happening here for this question. All right, if we start with that second derivative being 6x plus 2, this means the first derivative is going to be 6x squared divided by 2 plus 2x plus a potential number on the end, that constant. If I just tidy this up a little bit, it leaves us with 3x squared plus 2x plus c. and that's our first derivative. And we are told that that first derivative, when we substitute in a value of 1, it gives us an answer of 0. Okay, so we're going to use this statement. We're going to substitute 1 wherever we see an x. Okay, so we've got 5 there, so we're going to have c is equal to -5. What this means is that our first derivative is really 3x squared plus 2x. Now we're using this line up here to do this, but we're going to put in -5 as our constant. The next bit of information we're going to use is this, that says when the original function has a value of -2, the answer is also 0. So if we have the first derivative there, this means the original function is going to be 3x, and we're going to add 1 to the power, divide by the new power, plus 2x squared divided by 2, minus 5x plus maybe a constant on the end. Just tidying this up, we're left with x cubed plus x squared minus 5x plus c. And we know this had a little bit of information in the question that says when that original function has a value of -2 for x, it's equal to 0. So let's go and solve this. Okay, so -2 to the power, that's -8 plus 4 plus 10 plus c equals 0. This gives us an answer of c equals -6. So what we're going to do now is rewrite that line, but instead of leaving the c there, we're going to replace it with the -6, because we now know the value of that constant. Alright, we've nearly done. We found the equation of the original function. What we were asked to do was to find the value of the original function when x had a value of 3. So we're just doing a straight substitution, and we get an answer of 15. You may now go and try and do your homework questions, and remember you can always post questions to your teacher, Miss Edwards or I, on Google Classroom. Good luck.